So this is our new meter stick torque setup. Uses our fabulous new hollow aluminum meter stick, which is just super cool. You have to feel it to believe it. We all carry these around all the time here because it's just fun to have in your hand. It has good rotational inertia.
As a simple hand demonstration.
Yes.
Right?
Mm-hmm. So in this case, though, I'm using our new meter stick torque apparatus, which takes the classical meter stick torque, which just was a pivot and some little hangers, and classes it up a little bit because we have actually a ball bearing pivot here. So this pivot is new. It looks a little bit like a rotary motion sensor, but it doesn't have any internal electronics, yeah. It doesn't have any encoder or anything in it. It's purely a pivot. In fact, I call it bearings on a stick because you can stick it on anything and just use it for its bearings. In this case, we have it hooked up with the little meter stick holder that allows you to slide the meter stick back and forth through it. This has the unique feature of having a level on it. And in this case, I really need the level because I'm trying to make this meter stick level in my experiment just to make things easier to calculate. So I've got a hanging sign over here, 200 grams hanging on here. The mass hangers are exactly 10 grams. So we made them an even number so that they're easy to add into your experiment. So if this is an equilibrium, then the sum of all the forces equals 0, and the sum of all the torques equals 0. And I want to show you how we can get the mass of the meter stick from this. I know approximately what it is, but we'll see how it comes out in the calculation. So I've got this pushing down on here. Notice that this string is pulling up on the meter stick and causing a clockwise torque in your direction. No, counterclockwise, sorry. I'm backwards. Yeah, so it's a counterclockwise torque for you. Everything else here is causing a clockwise torque. As you can see when I hang this on here, it's pulling it down and counterbalancing that torque. But there's also a couple little hidden torques here. There's the weight of this hanger, which is 10 grams, and times G. And then the meter stick itself has weight, and it acts at its center of mass, which is at 50 centimeters. So just to here's the setup here. What I have up here is a tension protractor. It tells you both the tension and the angle of the force in the string. So
is that rod 120 centimeters?
Yeah, it's the longest one we have. I think it's 120 centimeters. And I backed it up with a shorter rod here just to make it a little bit more rigid. And I wanted to make sure that this was plumb so that my tension protractor up there would be giving me the actual angle. So that's measuring the angle from the horizontal. 0 is horizontal. And so it reads out this angle here. We're going to need that angle in our calculations down on the other end of this. Now, another feature of these little hangers is that they have an angle indicator built into it. So it's approximate, it's, every five degrees or something. But you can get a good estimate of what the angle is just by reading it off of here. So here I have a picture of just the meter stick and the forces that are acting on it. This is the force of the meter stick. This is the force of the hanger that's got the string on it. The string is pulling up that way, and the weight of the sign is over here. So as I said, so that you can follow along, this is 10 grams. No, I'm sorry. We don't know what that one is. We're going to find out what that one is. This one's 10 grams. This one is 200 grams plus the hanger, so it's 210 grams. I'm discounting the weight of the I love physics sign.
Have you taken your measurements yet? Can I make this vertical?
No, I haven't done anything.
Since we moved the table, this isn't vertical
It
anymore.
changed the, okay.
There we go. And that's what's nice about the double rod here, is it allows you
Well, also, when you're setting this up, before it's all set up, you can hang a weight straight down on the tension protractor to make sure that it's reading 0 to begin with. And then you can put the string on. So everything is leveled pretty well. And this force reads what? 5 point. The red arrow indicates the force, 5.3 newtons.
And the angle looks like it's right at 55.
55?
So where the string crosses the angle here.
That's where you read the angle.
So this is 55. Okay. So now we can set all of the counterclockwise torques equal to the clockwise torques. And the counterclockwise torques, I'm trying to think again of which way you're seeing. Darn it. Yeah, that's the up one. That's this one. So taking the force in the tension in the string times the sine of theta, because we have to have really just the component of the force that's perpendicular to, so we're actually taking this perpendicular force acting out at that distance. I'm going to define all my distances from the pivot point. So I'm just going to call this R1. And R2 goes to this one right here. And R3 is this one. Now my pivot is actually right on the 2 centimeter mark. So we can put that in here. I hung this at the 98 centimeter mark. And the other one is at, I can't see with these glasses, 67. Nice thing about these meter sticks is you can read them from both sides, and they read the same on both sides. So 67 is the mark right here. So you can see that R1 is going to be 98 minus 2. The lever arm is from the pivot out to where it's being applied, so it's 96 centimeters. And R2 is going to be 67 minus 2, so it's 65. And R3 is from the 50 centimeter mark, which you can prove to yourself by balancing the meter stick beforehand on your fingers till you find where they meet, or just balancing it on a knife edge.
So can you hide mass up in one end?
You could trick, yeah. If you have students that think they know it all, then since this is hollow, you can stuff something down in it and actually change where the center of mass of this stick is. So you can check on whether they really are doing the math. So this is at 50 centimeters here for ours. Nothing's hidden. So this is R is going to be 48 centimeters. So for this torque, I have the tension times the sine of the angle times R2. And then on the other side, balancing that, is the mass of the stick, which is unknown, times R3. And that's at a right angle, so the sine of 90 gives you 1. And then the mass of the hanger out here times R2 plus the mass of this hanging thing over here is M1G at R1. So you can solve this for the mass of the stick. Notice that the tension is in newtons. The tension protractor is calibrated to give you the force in newtons. Everything else we have is in grams, so you need to convert to kilograms and use, for these distances, as long as you use the same unit for all of them, you're okay. Technically, they should be in meters if you're trying to go for Newton meters for the torque, but the units will cancel out. So you could just use centimeters. And of course, G has to be in there. So if you calculate this out, and I'm going to magically calculate this. The mass of the stick comes out to be 150 grams. And voila, if you measure that, you will find that it is 150 grams. They're all approximately the same. You can find the approximate mass and the dimensions of this meter stick on the outside and the inside dimensions of the meter stick on the website. So you can make your own accessories for it. The other thing that is nice to do with students who are a little more advanced is to shorten this up and have this be at an angle like this, so you have like a crane. And so now you've got other angles involved, so you're going to have to measure what the angles are here. And it makes it a little bit more complicated. Now, back to this pivot. The pivot is designed to do regular meter stick torque. So normally you would have this slid through to, I can't get past there, slid through to the middle, normally use it on the stick. And it's designed so that the center mass of the stick is below the pivot point so that it's a stable equilibrium when you're doing that experiment. But, get rid of this. It is also possible to turn this stick pivot the other direction. So you can put it on a rod that's horizontal, vertical, do anything you want with it. And in this case, I've changed where it's attached so that it's attached in the center of the stick. So I can rotate it around like this. And so now I can do rotational inertia of this meter stick. I have mass in my pocket here.
As every physicist should.
Yes. You should see what's in my purse. I have a code node in my purse, always. And here I have, it's actually the axle goes through, so there's a place to put the meter stick, but there's also a place to put the pulley. And so you can use the pulley to apply the torque. And, all right, hold on. There. I've got it so that it'll hook. Thank you. Let me reach in here. I'm going to take some data, so let me reach in here and turn on this photo gate. This is, again, the wireless photo gate, smart gate. This pivot comes with this pulley so that you can use it in this fashion. And I've got to acquire that photo gate. There it is. Okay, so we're ready to go. And if you look at my screen now, I've got, are you seeing it? Okay. I've got the angular speed versus time. And I'm getting the angular speed from this pulley here. And so this is just a smart pulley. We used to call them smart pulleys, and we sold a separate product named that. But so this pulley is blocking photo gate number 1 on this. There's actually a dual photo gate here, but it's just using the one photo gate. And I can get the angular speed of this, which will be the angular speed of my apparatus. So let me just let it go here. Okay, I stopped it because I know it was going to hit the ground down there. You can see that this is a fairly straight line, and we can take the slope of it, and it comes out to be 1.65, which is the acceleration, the angular acceleration of this. Now, you can go ahead and use that to calculate what the rotational inertia is of a meter stick about its center. But rather than bore you with that calculation, I'm just going to do an off-axis thing here. I'm going to change where this is. I'm going to change this to 35. So now, instead of rotating about the center of the meter stick, I'm rotating about a point that is in a parallel axis, parallel 15 centimeters off. So the mass of the stick times r squared is the additional rotational inertia that you're going to get. And let's just try it out. Let it rip. Okay, I stopped it. So here you can see that the new pink line is at a lower angle because the acceleration is not going to be as much now. I used the same weight to accelerate it, but the inertia of the stick is much larger because it's off axis. So that's an easy thing to do. The other thing you can do easily with this is you can have it turned up like this. Let me just flip this around. Usually on these pulleys, well, it doesn't really matter actually. There are a complete set of rotational inertia stuff for our rotary motion sensor, where you can have a disc and a ring and point masses that are movable, and all of that fits right onto here without any additional equipment. So you can do the rotational inertia of all these objects as well. One more thing. As I said, the dimensions of this are on the website, and it is hollow. So the coolest thing is that you can also do a little electromagnetism with it. I have a dime here, and I'm going to drop the dime through here to show you how quickly it goes through. It's pretty quick. And then I've got a neodymium magnet, and I'm going to drop it through, and of course it's going to induce currents. It's falling. And you can see it took a lot longer to do that. And as the induced currents dissipate the energy of the magnet as it falls, then it's going to fall slower. Now, this magnet that I have just happens to fit down the tube, down the meter stick perfectly. That's because I own every type of neodymium magnet in the world. And I will point out to you that the magnets that we sell, the little ones, are quarter inch thick, and they're just a little bit too thick for this. So you're going to have to find your magnets elsewhere for doing this until I actually put one in there that we can sell that fits it. So that's it for the